Hi, Dennis. Great, so how does a particle physicist think? So the first thing, and this is probably the most annoying thing about particle physicists, but I'm going to get it out of the way because it's just something we do, is that we use natural units. So we set Planck's constant and the speed of light equal to 1. And I know this is sort of annoying, but it's actually really handy, and it helps us do a lot of shorthands. It means that there's only one unit, which is energy. So you can talk about everything in terms of energy units. Right, so setting speed of light equal to 1 is saying that I'm not going to distinguish between time and space. They're going to be the same basic thing, so I can use either unit to talk about space-time. And setting Planck's constant equal to 1 is saying that energy and distance are essentially the same thing. And one way to think about that is that if I want to talk about a distance scale, there's a photon that has that wavelength, and that photon would have an energy. So whatever the energy of the photon that has that wavelength, that's the energy I'm going to use to talk about that distance. So again, we talk about every unit we're going to talk about in terms of energy. So if I talk about a time, that's an inverse energy. If I talk about distance, that's an inverse energy. If I talk about temperature, that's an energy. All these things are an energy. So something just to I think, makes things really clear is like 1 Jansky is 2.4 times 10 to the minus 21 cubed. I don't understand what a Jansky is anyway. That's as much as I knew anyway. So, okay, so why would you ever want to do this? Just a little bit before we move on to other questions, why would you want to do this? Like, why would you say, here's the Empire State Building, which is 4 times 10 to the minus 10 EV inverse tall? That's not a very convenient thing because we don't have a good intuition as to why that would be a good way of talking about the height of the Empire State Building. But there are circumstances under which using energy to talk about distances is very handy. So for instance, let's suppose you have some sort of dwarf galaxy, and you look at that dwarf galaxy and you measure it and you say, well, maybe this galaxy has a size which is something like 10 to the minus 25 EV inverse. That's how big it is. Well, now we have an energy scale, which is also a momentum scale that we can now talk about. And so you can say, well, if I'm talking about very, very light dark matter particles, they act like waves and they have wavelengths, and their wavelength is characterized by 1 over momentum. And so if the momentum scale is comparable to this, then I can keep the dark matter particle inside of the galaxy. But if the momentum scale is too low and the wavelength of that particle is too large, then I'm not going to be able to keep the dark matter inside of that galaxy. And I'm not going to talk about this particular phenomenon, but this is just an example of why using energy units can sometimes give you a handle of very quick and easy comparisons between different phenomena to know whether or not they're going to be relevant or not relevant. So ultimately, I want to talk about cosmology and questions of cosmology. And one of the most important things in cosmology is Hubble, of course, just as in general. And so how does a particle physicist think about Hubble? Here's Hubble. This is Mary Angela's dog, Hubble. As you can see, Hubble is not into any tension at all. It's very relaxed. So how does a particle physicist think about Hubble? Well, first off, of course, there's the Hubble that we all learned when we first learned Hubble, which is Hubble's law, right? You go out, you measure a galaxy, it's got some recession velocity, there's a relationship between the recession velocity and the distance, and that's Hubble's law. And so Hubble is, of course, that number, right? So that's what the first Hubble that we all learn and use. But that's not the only Hubble. It's also a rate or a time scale, right? This is kilometers per second per megaparsec, so I can just convert my units, so I only have seconds left. And this turns into a time scale. And that time scale is about 14 billion years. And that's the time scale over which the universe changes by order 1, right? It tells us about how long the universe takes to change. And it's also an approximate measure of how long the universe has been around. It gives us the characteristic time scale for the universe to have been around. And as a consequence, it's also a distance scale. Because I can say, well, if the universe has been around approximately this long, then I send out some sort of sound wave or some sort of signal. What's the maximum distance that could propagate? And I could have interactions in that time scale. So Hubble is, of course, Hubble's law, but it's also a time scale, it's a rate, it's a distance, it's all of these things, and we have to keep all those in our head as we're thinking about cosmology. Another important thing is that Hubble, of course, is changing. Now, we have something we also know and is essential for many of the revolutions of cosmology in the last couple of decades, but it changes in a way that we can understand through the Friedmann equation. So the square of Hubble is just related to the rho, which is the mean energy density of the universe. And as the universe expands and energy dilutes, this rho goes down, and thus Hubble goes down with it. And conversely, as you go back in time, and as the universe is getting things closer and closer together, the mean energy density is going up, and Hubble back then was even higher. And importantly, that change in energy density is calculable. So especially if you go back to the early universe, and early isn't that early, just z of a few thousand, the universe is dominated by radiation, and you can calculate Hubble's constant depending on really just two quantities. One is the temperature of the photon bath and the number of particles that are actually around participating in thermal equilibrium at the time. So this gives us a really powerful, given if we go back to this idea that Hubble is a time scale and it's a distance scale, this gives us a really, really important connection, because this temperature, if you say, I'm talking about the universe at a temperature of 1 MeV or 1 keV or 1 GeV, that temperature then tells me Hubble, and Hubble tells me all those things, how big the universe looks, how old the universe looks, all those things get told to me simply by specifying the temperature at any one time. So let me just really emphasize this, because this is going to be critical for as we think about different eras of cosmology, is that at any given time, the universe has some temperature. And we can talk about it in terms of its temperature. We don't even need to talk about how old the universe is. We can just talk about what temperature it has at that time. But that then tells us H. That tells us we can calculate Hubble by knowing the temperature. And if we know Hubble, then we know how big and how old the universe is at that point. And that gives us a direct mapping between temperature and size. So what does this do for us? Well, we know that a lot of different physics changes as a function of temperature. We know that at high temperatures, for instance, quarks are free, and at low temperatures, they bind up in protons. We know that at high temperatures, there's top quarks and bottom quarks and all sorts of things around. And at low temperatures, we just have electrons, photons, and neutrinos. And so as you go from different eras of the universe where different particles are around, where different laws of nature are at play, those laws of physics and particles get imprinted on the properties of the universe, on the cosmological properties of the universe. So one way to think about this, right, is let's suppose that I have some sound wave of some particles that starts here and it's propagating out, and at some point those particles all decay and they're gone. They can turn into some other form of radiation. Well, if I look at distance scales which correspond to this distance scale, I can see an imprint of the existence of those particles. But if I look at very, very long distances, then that gets entirely washed out, and I won't be able to see those signals anymore. So the short answer of this is that as I look at smaller and smaller distance scales, I'm seeing the properties of the universe when it was at higher and higher temperatures. And this is a really, oh, I didn't want to do that. This is a really critical correspondence. So that then brings me to the title of my talk, which is the desert. And the desert I'm talking about is actually the LCDM desert. So what is that? So this is a plot of most, not all, but most of the fundamental and some derivative energy scales in the standard model. So energy along this axis, and this axis means nothing. So at the very top here, you have M top at 174 GeV. Then you got the Higgs mass, the Z mass, W mass, B mass. You got a whole bunch of hadrons in here, different quarks, other leptons. Then you get down here to the temperature around an MeV scale, where you get to the electron mass. The electron mass that's right here. And then you have this big gap. And then you get to approximately an EV scale where you have matter radiation equality, the cosmological temperature, where matter and radiation have the same energy density. A bit below that, where you have recombination and also the heaviest neutrino mass, and then the next neutrino mass, and so on. And what's really interesting from a particle physicist point of view when you look at this is this period up here is extremely dense in energy scales. And down here, it's also not as dense, but there are definitely energy thresholds and transitions you're going through. And we have this tremendous gap where nothing really happens from a particle physics point, where particle physics is extremely simple, where nothing new is appearing, nothing new is changing, stuff is going out of equilibrium. The particle physics is something that we can understand extremely well in here. And that gives us an opportunity because if there's lots of stuff going on, then that's almost like noise that you have to filter out. Here, the particle physics is very clean. And this is what we refer to as the lambda CDM desert. It's a desert, not in space, but of energy scales where nothing really should be happening. Okay? Nothing interesting is happening there, which means if something interesting is happening there, it's very interesting. So what's in the desert then? If I say nothing's in the desert.
That's on a log scale. That's on a log scale.
That's on a log scale, yes.
So why is that? I mean, if you didn't plot on a log scale, you wouldn't see that.
That's true. You would not see that. Physicists, I think, tend to think of order of magnitudes, which naturally, exists on a log scale. So, yeah. Also, I guess another point is that if you think cosmologically, right, every sort of Hubble time, you're essentially changing typical energies and things like that by a factor of 2 or so, right? And so if you think in terms of cosmological time, it really is a logarithmic scale that tells you sort of like how things are changing if you measure it in Hubble times. So what is in the desert? Well, what's really exciting that's in the desert is data. And this is why it's an interesting thing to think about. So here are just some data from a variety of galaxy power spectrum, CMB power spectrum, polarization data as a function of multipole or wave number here. And what I can do is I can say, well, let me go to, say, this distance scale here, about 10 megaparsecs. There was some point in the history of the universe when that was the size of the universe, okay? When a sound wave could have traveled that distance, and that was at some very particular temperature. So distances that are shorter than this are sensitive to physics that was, higher energy than that, and distances that are longer than this are not sensitive to those temperature scales. And I can make a sort of correspondence. So these then end up being the energies that these different wave numbers are sensitive to. So at, say, 1 megaparsec, that's sensitive to temperatures of the universe that are smaller than about 100 eV or higher than about 100 eV or so. When you are down here at 10 to the minus 3, so 10 a gigaparsec, then you're talking about fraction of an eV and up. So this wave number scale, this set of distance scales, maps onto a region of energy scales, of temperature scales, where we can learn about what kinds of things were going on early in the universe. And you can do the same thing with the CMB in terms of multipole, and it's also a very similar set of energies. What's also exciting is that it's not just the data we have, but it's, of course, the data that's going to come. We have upcoming CMB experiments. We have more data that we hope to get from ACT and SBT, but of course, Simon's Observatory, maybe CMB-S4 is not going to give it to us, but advanced Simons hopefully will. But we have a tremendous amount of data which is coming. We also have a lot of data from, it's not even appropriate to call it large-scale structure anymore, but really looking at the microphysics of galaxies and getting understanding of what kinds of dynamics are happening at small scales in galaxies, and you can ask the questions about those related to temperatures as well. This is from this Snowmass white paper talking about using cosmology to look for new physics, and they actually did a much better job of mapping this out. So here you have the temperature of the universe in EV when the Hubble size was equal to this particular scale, and you can see that this coming era, when we start studying, say, for instance, power spectrum of streams, or looking at the properties of subhalos, these things are going to be really taking us into this range of, say, like 10 to the 3 to 10 to the 5 EV. So we're going to be getting a lot of information and a lot of data that's going to be telling us about this desert. And so if you are about to fall asleep and you're just clinging to consciousness, the one thing that you should remember is that this era, from a particle physics point of view, from a cosmological particle physics point of view, is an era of the desert. This is the era where we are going to get a tremendous amount of information, which is going to tell us what kinds of things, what kinds of particle physics could have been going on in that EV to MEV era. That's not the only thing. It's not just data that is in the desert. Anomalies are in the desert also. Since we're all at CCA, it's impossible for you not to have been about 18 to 20 talks in the last week on the Hubble tension and SA. But there are these exciting tensions, right? So we have the Hubble tension, which is, at least in some forms, a tension between the late universe Cepheid normalized expansion rate measured by a supernova versus early universe measurements of the expansion rate, or early universe inferred measurements of the expansion rate. And you have the SA tension, which is up until recently also been a tension between the early universe inferred measurements of what the power at 8 megaparsec scales is, and the late universe measurements of 8 megaparsec scales, which is also a tension. And as it will turn out, because these scales these measurements rely on physics which is in the desert, desert physics is really important for possibly addressing these tensions. So, irrespective of anything else, I think there's a lot of possibility in the coming years, just from the fact that we have these new data coming, to constrain or discover physics that's at or below the MEV scale. And the presence of these anomalies, I mean, you can take different attitudes about anomalies. You can be an optimist and hope they bear out. You can be a pessimist and say these things tend not to. But they give us concrete targets to think about. And empirically, physicists are more creative when they have concrete targets, and they help us motivate new models as well. So if that's the data situation, if we say, okay, we're going to have all this great data, and that these distance scales, these angular scales that we're going to study are going to sort of directly probe the properties of the universe at temperatures of 10 or 100 EV or KEV, should there be anything? I mean, your sort of natural reaction to this is to say, look, the electron is half an MeV in energy. If I convert it to energy, it's mass. Don't we know about physics that's below that already? Haven't we done all sorts of colliders that have studied all of these things that make us feel extremely confident that there's nothing that's going to happen below an MeV? And that's the next question I want to address. So let's rewind a little bit. This is this really plot that everybody, if you go to a cosmology colloquium, this is the plot that you're like legally required to show, where you say this is dark energy and this is dark matter, and then there's baryons, and you say, look, what a small fraction of this. And then you maybe don't even mention the photons are neutrinos here, and you say, wow, the universe is dark, we really need to understand that, which is true. But if you rewind the clock and you say, well, what would somebody in the desert have said? Well, this is what the energy budget would have looked like at, say, a Z of 100,000, okay? Dark matter is irrelevant. Dark energy, what energy? It's all about neutrinos and photons, okay? And photons we have understood pretty well and studied it experimentally pretty well, but neutrinos we have not, in the sense of really having accurate information about the properties of that neutrino bath. We're still at an early stage of getting understanding of how this stuff behaves. And so it is really an open question if this is neutrinos or if it is something else. So the experimental windows that we have on the desert, you can kind of look like this. So here's the EV scale and here's the MEV scale. you kind of come at it from both sides. The CMB today kind of probes this energy range and will push up to maybe 100 eV. Large scale structure is kind of probing up into sort of like 10-ish keV range, and in the future is going to probe up even into the 100 keV range. The boundaries here are not really clear, and like I said, it's not even, if I have a plus, because it's not even really appropriate to talk about as large scale structure when you're talking about streams and things like that. And then from the high energy side, well, it's a very different set of measurements, but you can go out and measure the amount of primordial helium, lithium, deuterium that exists, and that gives you a great deal of information about what kinds of particles are around at this temperature. And something that I'll talk a little bit about, but won't have tons of time, is that even this is not a, you might think this is a done question, but even by getting more experimental data, we might be able to push this BBN window down below 100 keV. So let's talk about what can happen in the desert. What kinds of things can happen? So I'm going to start by talking about things which have been around as ideas for a long time. Okay? So these are classic ideas of what could happen in the desert. One classic idea is relic radiation. So what does that mean? Well, imagine that at some very, very, very high temperature, the standard model was in thermal contact with some other stuff. They shared energy and entropy. And then as the universe cooled down, somehow these sectors decoupled from each other. You can kind of look now, and not that long ago, neutrinos and electrons were all part of one sector. And then at an MeV, they separated from each other and stopped talking. So you can imagine something like that happening at a very, very high energy scale. There's some other particle that's in thermal contact, and these things separate. And then the standard model, so this dark sector maybe has one particle, just for simplicity's sake. And the standard model has 100 particles, right? At least if you're counting degrees of freedom. It's got tops, bottoms, charm strange, got all sorts of vector bosons, gluons, all these things. And so all those particles are over here. And as the universe cools down, they increasingly dump their entropy into the lighter and lighter particles, heating those particles up. So at the end of the day, the electron today, well, the photon today, has much, much, much more energy than that dark sector particle, which never got an additional heat. So you can kind of think about this schematically. You start with some sort of unified sector of standard model plus this particle phi. You split it at some point into two sectors. Then as the standard model cools down and this sector cools down, all the many degrees of freedom that you start at high temperatures get dumped into the light degrees of freedom, heating them up. And so this sector ends up being much hotter than this sector. And so this looks like a very, very, very small amount of radiation left over compared to the standard model. This is a sort of very nice way of representing it, which is that you can think of, say, the lightest, this sort of like least number of degrees of freedom particles, this Goldstone boson, which is here. And you can say, well, how much does it influence the universe that we see today? Well, it depends on when it and the standard model separated from each other. So if they separated out here at 10 to the 6 GeV, so a very, very high temperature, then the standard model had all of its degrees of freedom that could kind of go into heating up the light particles. And so as a consequence, this particle is a very, very small contributor to the energy density today. On the other hand, if it separated from the standard model at late times, then it could be a very large contributor to the energy density today. And the way that we quantify that and that everybody talks about that is in terms of this quantity here, delta N effective. And delta N effective is the change in the number of relativistic degrees of freedom. So we think that there should be three, namely 3 neutrinos. And so if you went out and looked and you had some Goldstone boson, it would contribute an additional 0.027. You can't really see this, but it's 0.027 to the energy budget today, which is a very, very small amount. But this is an old idea. This is something that's, a critical goal for many of the ongoing CMB missions to try to find whether or not there is any additional radiation, even a tiny amount of radiation left over from the early universe. Now, radiation has big influences both at late times in terms of changing the properties of matter or matter radiation quality, as well as influencing BBN. So in terms of influencing BBN, Big Bang nucleosynthesis, it has a sort of roundabout way of doing this. You have additional, if you have delta N effective, that means you have more stuff. More stuff means Hubble is larger. Larger Hubble means the universe is expanding faster, which means things kind of happen faster. And in particular, protons and neutrons decouple from each other faster, which leads to more neutrons, which leads to more helium. It's a very roundabout process. I don't want to take us through the whole argument here because it is pretty detailed. But the important point is that just the fact that we go out and measure the amount of lithium, deuterium, and helium tells us a lot of information about how much radiation was present at an MEV, and in particular that it shouldn't be too much. So let me introduce another classic idea of sterile neutrino dark matter. Sterile neutrino dark matter is actually a really beautiful idea. At this particular point, I think it probably doesn't, at least in its original forms, work. It's confronted by a combination of X-ray data and structure data, dwarf galaxy data. But it's a really beautiful idea, and it really should have been right. I didn't come up with it, so I can say that. But so let me take you through how sterile neutrino dark matter works in its classic fashion. So to understand that, let's talk about something that in particle physics we call mass mixing. So any state with the same charges can mix with any other state with those same charges. So for instance, in the standard model, you have the up quark, the charm quark, and the top quark. They all have the same electric charge, they have the same color charge, they have the same spin. And so there's nothing that can really distinguish them from each other. And so a charm can turn into an up. It just can't. There's no conserved charm number. You can have a meson that starts with a charm and ends up with an anti-charm. There's nothing that stops these particles from turning into each other as long as you conserve other things like energy, which you can do in meson systems. Likewise with the bottom quarks, downstream and bottom. They all can convert into each other because they have the same charges. Same color charge, same electric charge, same spin. They can convert back and forth. The most famous one that, of course, we know about, and from a sort of like a cosmological point of view, is neutrino oscillations. So neutrinos have no electric charge. They have no charges that we know of, except for the fact that they're spin 1/2. And so you might start with an electron neutrino, but there's nothing to tell you that it can't turn into a muon neutrino, or a tau neutrino, or vice versa. And it's really just this quantum mechanical statement, which is that if there's nothing that fundamentally tells you that this thing is different from that thing, then they can convert back and forth. Right? If there's no conserved quantity that tells you you can't change them, quantum mechanics will change them. It will do it. So you can then say, well, look, all these things have standard model charges. They have electric charges, they have color charges, and we've gone out and looked, and I know there's nothing with a big electric charge. It's a charge 1 at an MEV, aside from the electron. Okay, there's no particles out there that are going to mix with these things. But the neutrino is sort of special because it doesn't carry any electric charge. If there were an uncharged dark state out there, the neutrino is capable of turning into it, and it's capable of turning into the neutrino. They're capable of going back and forth between each other because there's no quantum number that stops that from happening. And so you say, okay, maybe there's this extra dark neutrino that we're going to add here, or that exists somewhere in the laws of the nature. There is some other fermion that has no charges, and it can mix with our neutrinos that have no charges. And something that Kev Abazajan likes to point out, who was one of the people who was very early working on sterile neutrino dark matter, is that it was a real political error to call these things sterile neutrinos, which I think we can agree was a terrible, terrible name. And that if instead it's called this a dark fermion, the citations would have been like factor of 4. So we're going to call it dark fermion, sometimes anyway. So how does this work? So the way this kind of works diagrammatically is you start off with a standard model neutrino, and it just kind of cruises along, minding its own business. And then there's some sort of process which has dimensions of mass that then turns it into this dark fermion. Okay, And we call that a mass mixing. So it's just some quantity that's in the theory that tells you how strongly these particles can convert amongst themselves. And you can say, well, how do I know if this is a big number or a small number? Like, what tells me that I should care about it? And the answer is that you want to compare this number to the mass of, say, this particle. And you take their ratio. And you call that a mixing angle. So the mixing angle between these two states is the ratio of this term divided by the mass of that guy. And so if this mixing angle is big, then this interconversion is going to happen a lot. If this mixing angle is small, this interconversion is going to happen very, very rarely. So now let me take you through, with that in our mind, this idea that these things can mix with some mixing angle. Let me take you through how the sterile neutrinos are supposed to be produced. And this is the original work of Dodelson-Widrow. And again, like I said, this particular mechanism doesn't work anymore, but there are lots of sort of variants that are sort of within the neighborhood of this model that still do. So what happens? You start with a standard model neutrino, okay? An electron comes along and it scatters off of something and it turns into a neutrino. So now I've got some standard model neutrino, and that standard model neutrino is flying, happily minding its own business, but it mixes with this dark fermion, and so it oscillates. So it's just cruising along, it oscillates, and all of a sudden it gets over to here, and it's no longer a standard model state, it's now some linear combination of standard model and dark states. So it's cosine theta standard model, sine theta dark. And then this mixed state continues to propagate until the universe makes an observation. Because the universe is going to ask the question, are you a dark state or are you a standard model state? And it does that by trying to scatter. So it sends an electron in, the electron flies near the neutrino, which we don't know what kind it is, could be standard model, could be dark. And if it can scatter, if it scatters, then the universe says, okay, aha, you were a standard model state. If you do not scatter, and you don't scatter enough, then the universe says, okay, I made an observation that you were a dark state. And so this is, if you think about this as a quantum mechanical experiment, you start with some state, it turns into some other state, which is a linear combination of two states. Then you do the experiment, you make the observation, and when you make that observation, it either becomes a dark state or it becomes a standard model state. At this point, you have some probability sine squared that it's dark, you have some probability cosine squared that it's standard model, and then you repeat the process. Just do this over and over and over again. Standard model oscillates, observe. Find out what it is. Goes through, oscillates, observe. Oscillates, observe. Again and again and again and again. And so the rate at which you actually take standard model stuff and turn it into dark stuff is very, very simple. It's basically just how big this mixing is times how fast you're making observations. And that's it. It's actually a very simple formula. And so you can just calculate this and find out how much sterile neutrino dark matter you're making. Except I'm lying to you. And I'm lying to you because I said that this neutrino is just freely propagating through space, and it's not freely propagating through space. This is the early universe we're talking about. The universe is full of stuff. Okay? It's not at all freely propagating. I have made a diagram here so you can see what it looks like. This is the neutrino propagating through a finite temperature bath. And neutrinos actually do get finite temperature, finite density corrections to their propagation, which you can kind of think of as like an effective mass. And so when I said that this mixing angle was the ratio of this divided by the mass of the particle, it's actually the ratio of that divided by the mass of the particle plus all these finite temperature corrections. Okay? So when you go to the really when you go to the very early universe, these finite temperature corrections become really, really big, which means that this mixing angle becomes really, really small. So you go back to here, cross out freely, and you say in matter. And the only thing that you have to change about this is that you change this formula to, instead of the mixing angle, you change it to the mixing angle in matter. Okay. So that there's still some probability to oscillate, but that probability to oscillate is changing as temperature changes because this mixing angle is actually changing as temperature changes. Okay. But aside from that, the story is good. So what that means then is if you kind of think about the evolution of the universe, if here is hotter, and here is colder, this is time. Well, the mixing starts very small and then increases until it gets to some asymptotic value. The scattering rate starts at some high value and decreases as the universe cools off. and the combination of them goes up and comes down. So there's some peak value that you can calculate, and that's when all the stuff gets made. So the comparison people like to make is of this rate compared to Hubble. So if neutrinos, if these dark sector states actually exceeded Hubble, then they would have come into full thermal equilibrium and you would have hot dark matter. If they don't come into full thermal equilibrium, then you just get whatever is at some peak point, and that is your warm dark matter. And this is essentially the mechanism that allows sterile neutrino dark matter to be produced. And it's a really beautiful idea. It's a very simple idea. It doesn't rely on any sort of elaborate new physics. It's just saying, let's suppose there's some neutral state that can mix with standard model neutrinos. What happens? It just turns out that that's not describing nature. So is that it? We need to go beyond the classics, I think is the point, right? We need to go beyond the classics. And so you can look at me and you can say, do you have a model, like a specific model? And I say to you, well, I have a concept. And I think that's where we really want to be, right? Because the odds of any particular model being right is pretty low. So you're asking the question, are we capturing some of the relevant physics of a model that might be right, okay? So the kind of physics that we want to do, though, is we want to take the classics. We take a sterile neutrino, which we all know is a classic. We want to take this gravitational radiation and just say, well, what happens if they hang out together? What if we take those two classics, peanut butter and chocolate, and make something even better? And the other thing we're going to do is we're going to allow that dark fermion to talk to this radiation through some interaction. But aside from that, that's all we really want to talk about, okay? We're just taking very well-known, established scenarios of particle physics and saying, well, what happens if we kind of mix these things together? Because who knows what's in the dark side, right? Well, it turns out that this actually changes that story considerably. So remember, this was the equation that told us how standard model particles converted into dark sector particles, that it was this mixing angle in matter times the scattering rate. But in the standard model, the scattering rate was just scattering off of standard model particles. And this mixing angle was just corrected by standard model finite temperature effects. If there's a dark sector around which has some additional radiation, then the dark sector can correct this, can also change this mixing angle. And the dark sector can also correct this scattering rate. And it's an open question whether or not dark sector effects or standard model effects are actually going to be the more important one here or there. And this is, again, nothing particularly new. This is something that was pointed out by Dasgupta and Kopp, who were really interested in trying to understand whether or not you could have sterile neutrinos that appeared at long baseline neutrino experiments consistent with cosmology. Brigman et al. Studied something like this in the context of scattering to see whether or not you could get sterile neutrino dark matter to come back. Here we just want to ask the question, let's just take this modification and see what happens. So what happens is actually quite interesting. So here's the temperature of the universe, and here's time. And I'm going to track the temperature with the temperature of, say, a standard model neutrino. So it starts up here, and there's a log-log plot, so it's nicely falling off as we go this way. Okay. But then there's this dark sector. Dark sector, some process is going to produce this stuff, and it doesn't really matter how much is produced, if any is produced, but it's hard to have these sorts of things where there's not some stuff that's produced earlier. Some stuff is produced earlier, fine. And then it starts diluting, just like the standard model neutrino, right? So as the universe expands, neutrinos cool off and they become less dense. Same thing would happen in the dark sector. The universe expands, these things dilute and cool off. But then something really interesting happens if you actually work through the physics. That this combination of oscillations and scattering becomes important. And it corrects this evolution. And it starts feeding energy from the standard model into the neutrino sector. And it's almost flat, the temperature stays almost flat until it reaches the point where these two sectors come into contact with each other, and then they equilibrate. At which point, you now have a complicated dark sector or neutrino sector that then continues to dilute until such point where the sterile neutrino becomes massive and it goes away, and the sectors decouple. To prove to you that I'm a serious person, here's an equation. This is the scattering rate, including all these different terms, compared to Hubble. And what you want to do, so the question that people always want to ask if you're a cosmologist is, when does the scattering rate equal the Hubble rate? When does the production rate equal the Hubble rate? Because if the production rate equals the Hubble rate, that means if I wait one universe's age, on average, every neutrino will have an opportunity to convert into a dark sector particle and vice versa, and those sectors will equilibrate. So that's why you set this ratio to 1. And if you do that, you get this, and then you get this, and then this is actually the thing that I want to pay attention to. If you say, just this, there's a dark sector. It's got a fermion. It's got an interaction. It can talk to us. It can mix. What happens? The answer is it will equilibrate in general. When will it equilibrate? It will equilibrate at this time. So the temperature of equilibration is approximately equal to the mass of the dark fermion times this. Okay, M Planck is a big number, theta is a small number, but you have this 1/5 power in here, which is really, really important because something we all know about 1/5 powers is they take big numbers and they make them into small numbers. And that happens here as well. And so this factor here typically is not too large, as big as 1,000, but oftentimes more like 10 or 20, something like that. So what you end up finding is that if there are dark states that are light, they will naturally equilibrate and they will naturally thermalize near their mass. So they're not going to come in equilibrium at very high temperatures and then lead to corrections to Big Bang nucleosynthesis and all these things. They're going to come in at late times, and they're going to have much more subtle consequences in terms of the BBN and the CMB and large scale structure. So the cosmological history looks something like this. You have at late times electrons, photons, and neutrinos. They separate from each other into just electrons and photons and just neutrinos. And then the dark sector could come into equilibrium, do all sorts of interesting things, and then come out of equilibrium as well. So if, aside from the movies and the fact that the desert is exciting, you have a takeaway, this is the other takeaway, which is that it's actually extremely easy to envision a scenario where a whole sector of physics comes into equilibrium with the universe at late times, not at early times, but at late times. And then the consequences of that dark sector will be imprinted on cosmology. And this happens even for mixing angles, which can be 10 to the minus 11, can be tiny, tiny, tiny mixing angles. You're not going to get any sort of signal in terrestrial neutrino experiments. Cosmology will be your only signal. So what kinds of signals can you get? It can cool neutrinos off, affecting Big Bang nucleosynthesis. It can introduce a new bath of interacting radiation, which has implications for the CMB. It can provide a radiation bath for dark matter scattering. So it could be this stuff, dark matter's out there and scattering off this stuff and impacting large scale structure. And it might introduce new mass thresholds in the desert. So I told you there's no mass thresholds, no mass scales in there. This sector could have a mass scale in that desert, and those mass scales can have interesting consequences. So let me very quickly talk about a couple of implications. So, so what kinds of things can we learn about this from BBN? So a very quick aside, there's 2 public codes that you can use for BBN. Actually, now there's more. There's a better one. Don't use these. Kara will tell you. But there are differences in what types of reaction rates they have. And they do give you different answers for predictions of light element abundances. And at this point, there's not an obvious thing where you can be like, they're right, they're wrong, they're wrong, they're right. You really need new data to distinguish between these. So that's just a caveat about these. So you can look at the production of the helium as a function of omega B and N effective using these 2 codes. There's a plot Kara made for me. Thank you, Kara. Compared to the data of YP, which is the amount of helium in the universe. And you can see that they're in pretty good agreement, although if you actually put the Planck measurements of omega B on here, it looks like Parthenopy is in better agreement than Fremont, but it's not a huge tension. I'm not going to spend much time there. So what happens when neutrinos equilibrate with this dark sector? Well, energy is conserved, not entropy. This is not an equilibrium process. So Hubble doesn't change. You basically just take particles that were in standard neutrinos and you kind of send their energy over to the dark sector. But when you do that, the neutrinos cool off. So if you think about how BBM works, there are some important energy scales to think about. At about 2 MeV, neutrinos decouple, so they separate from electrons. At 1 MeV, your neutrons and protons have been interconverting, and that stops happening. At half an MeV, electrons go from being relativistic to non-relativistic. At 0.1 MeV, there's a process called the deuterium bottleneck, which prevents the formation of heavier elements. And at 0.05 MeV is deuterium freeze out. So it's important that there's a lot of actually different scales. We usually only talk about, if you take a particle physics class, people only talk about this. There's actually a lot of scales that come into play in BBM. And so what can happen is, perhaps you thermalize in here. Well, if you thermalize in here, you're going to cool off your neutrinos, and that's going to have consequences for the production of deuterium later. So this is analysis that Kara, Martin, and I did recently, where you can look at, among other things, the effects of this neutrino cooling. And one thing that you find is that if the neutrino that you're mixing with is mostly mu or tau, so it doesn't have a lot of electron content in it, which is this case, then you can actually equilibrate up to fairly high temperatures. So this is the temperature which you equilibrate, and this is a measure of how much energy you take out of the standard model. So this is taking all of it, this is taking none of it. But if instead you actually are equilibrating with an electron neutrino, the limits are quite strong. So even if there's a little bit of electron neutrino, like half an electron neutrino that is mixing with you, then you have really important consequences for Big Bang nucleosynthesis. And this temperature of equilibration has to be lower than about 100 keV. How about at later times, at lower temperatures? Well, if this sector, we have this dark fermion, it has a mass, you're going to go through that mass threshold. When you go through that mass threshold, something very interesting happens. So you start at a high temperature, you've got sterile neutrinos and all your other particles, and then you go below the mass of the sterile neutrino, and that sterile neutrino has to dump all of its entropy into the remaining light particles. When that happens, those particles heat up, and that effectively leads to a change in N effective. Okay, so one of the consequences of a mass threshold is you have the energy density of the dark sector coming down, it then kind of comes up a bit and then continues to dilute. And that means that N effective is not just some number, it's actually a time-dependent number. It's a temperature-dependent number. So it's not just one thing you can put into the code and forget about it. It actually changes with a function of time. Moreover, if dark matter, say, is out there and dark matter is scattering off of the sterile neutrino, if these sterile neutrinos go away, that can stop dark matter scattering. So you can have a situation where dark matter was not CDM at early times, it was actually interacting, but at late times, its scattering partner has gone away or become ineffective, and thus it turns into CDM at late times. So let's talk about the Hubble tension very quickly. So the Hubble tension, remember, is the disagreement between the late universe measurements of how the universe is expanding versus the value that we infer using a set of cosmological data. And this is a very hard problem. And I mean that I think, including what I'm talking about here, I don't know, personally, and I could be wrong, I don't know of anything that I look at and I'm like, ah, that's the particle physics explanation of the Hubble tension. I don't know of something where you like do the analysis and then you're like, yes, that clearly works. Everything now lines up. It's just perfect. I don't know of that model. But I know of things that make progress on it, and I think that that's an important thing to do. How hard of a problem is it? Let me just emphasize how hard of a problem it is. Okay. This is a paper that came out earlier this year. A bold proposal that possibly the Hubble tension could be solved by changing the value of pi. All right. So they did this analysis, and they found that by allowing a slightly higher value of pi, indeed, you could fit the Hubble data. But they were not careful. If you actually go into their data and their fit, you see that they have an extracted value of the amount of baryonic energy density in the universe of 0.00 or 0.025. If you go back to this plot that Kerr gave me, right? This is an effective, right? So you want to live on the standard model line here. This is omega b. These are the two theory predictions. They're telling you that they want omega b to be over here. If that were true, the helium production would be so high, we would know it. So I think we can experimentally say that this is not the solution to the Hubble. That's just showing you how hard it is to solve this problem. And you can relax pi, and you still run into experimental conflicts. We're going to be writing this up soon. So how does the Hubble tension work? There's this formulation by Euler et al. From 2019, which I think is the nicest way of talking about it, where they say, look, this acoustic peak in the CMB is some angular scale. And that's set by how far a wave traveled at that time. It's the largest pressure wave that could propagate at recombination. So there's some observer looking at the CMB. There was some sound wave that traveled out, and it's some distance away. And so that angle is just a ratio of this length divided by this length, okay? But remember, this length, how far away that is basically a statement of how old the universe is. So that's just set by the Hubble parameter today. This is set by how old the universe was then. So it's a ratio of how old the universe was then to how old the universe is now. So it's a ratio of Hubble then to Hubble now, or inverted. And so this is sort of like how it was turned into a horizon problem. And thinking about, well, maybe the problem is not about our late universe physics, but about changing how fast the universe was expanding then. Because if the universe was expanding at a different rate then, if Hubble back then was larger, I can make Hubble now larger too. That was the point that was made even before this paper. But this paper, I think, phrased it like in this way. So recent collaborators, as soon as the Hubble tension appeared, they noted this. They said, look, additional radiation back then, if you have enough of it, could change the expansion rate of the universe back then and could change how we infer the Hubble constant now. And then all the data sets would be in agreement, which is a great proposal. The problem is that the data have gotten better and better. And at this point, it doesn't really work. There's too much tension between this proposal. So a quick comment on BBN is that when people include additional radiation in these models, they usually assume that radiation was always there. And then as the universe then proceeded, that then changed the amount of helium. And so you get two effects on your CMB. You get an effect on the CMB because you have additional radiation, but you also get an effect on the CMB because you're assuming you made additional helium at early times. And so there's two factors that are at play here that really should be separated, and I think it's important people separate them. So we went and did an analysis of what happens if there is this change in N effective during this sort of era of CMB data, so in the late desert era. And we found that there's actually a pretty moderate, if you include the shoes data, preference for some change in delta N effective at Z of around 20,000. It's not super strong, but there is some evidence that the data would prefer something like this. So you can kind of go step by step about how the model fits the data better. You can start with lambda CDM, and then you can add N effective, and you actually improve the fit by a little bit, by a chi-squared of about 6. You can then allow that radiation to have self-interactions, so it scatters off itself. That improves it further by about 5. And then you can allow it to have some transfer, some change in N effective, and that improves the fit by an additional few. So I don't think that this is some like smoking gun that there's a solution here, but I think it's clear that there are models that have dynamics in this desert era that look like they can get the Hubble tension to at least be ameliorated. What about S8? Well, S8 is a disagreement between various measurements of the amplitude of fluctuations at the 8 megaparsec scale. So you can do your CMB analysis, and you can sort of extrapolate in lambda CDM to 8 megaparsecs. You get a value, or you can go out and directly measure it or measure something near it using galaxies. Or importantly, you can more recently use CMB lensing to detect the presence of structures between us and the CMB. And so at this point, all these values seem to be in agreement with relatively high SH, while sort of measurements of structure look like they are getting a low value. And I think that once these ACT CMB lensing measurements came out earlier this year, I think a lot of people said, well, we're done. We're done. We don't need to talk about this anymore. But what's important is that all these analyses were done in the context of lambda CDM. And so here is a plot by Gerbino et al., which tells you how the kernel of weight from different redshifts and scales fits into any individual measurement of S8. Nobody goes out to 8 megaparsecs and looks at 8 megaparsecs and says, how much fluctuation is it right there at 8 megaparsecs? You do some combination of measurements over redshifts and scales, and then you put that into a model and you extrapolate it to this 8 megaparsec scales. And what you see here is that CMB lensing is at relatively large scales, galaxy density is a relatively small, cluster count's also relatively small, whereas the actual window function from S8 is right here. So you can see that we're really taking lots of information from outside S8 and extrapolating it into S8. And so in lambda CDM, there's attention, but it may not be that in other models there's attention. So you can imagine, say, dark matter might be scattering off of this radiation bath, but then you go through this mass threshold and the interactions turn off. Okay, so at early times, dark matter is scattering. At late times, there's nothing to scatter off of, or the scattering becomes inefficient and turns off. And so you could have a scattering rate. So here's the scattering rate of dark matter compared to Hubble. And it might start very high at high redshift. And then as time goes on, the scattering rate drops, and eventually it becomes very small. At the same time, at early times, all the scattering prevents the growth of structure. So the power of this model is reduced compared to CDM. So over here, the power is reduced, a lot lower fluctuations. But as the scattering becomes inefficient, this returns to a CDM-like behavior at large scales. So if you fit in this model the data, and so here the data are Planck, ACT lensing, Pantheon, and the BAO data from BOSS. What you find is, so here is lambda CDM with a very, very tight measurement of S8. And you find a much broader fit to S8 in this model. So it's clear that in a model like this, the overall ability to consider suppression of power at smaller scales is significantly enhanced, which then suggests to us that this is not a data-to-data conflict. It's really a data-to-data conflict within lambda CDM. And I encourage you to talk to Tony about this. So is this telling us that I have got up my concept of a model is that dark radiation is solving the Hubble and S8 tensions? And my answer to that is it doesn't matter. I mean, it does matter because it was cool. But that's not really the point, right? The point is that there's actually a lot of freedom in the types of physics that could happen in this desert era. There's a lot of modifications beyond lambda CDM, beyond N effective, that can happen in the desert. And those signals are going to be constrained by future data. We're really going to learn a lot about it, but we need to think about it now because you can't ask these questions without actually having models to study. And so that's the real conclusion. This is the era of the desert. We have upcoming data sets that are going to give us a tremendous amount of insights into what's going on during this desert era. That very, very simple models that you don't need to go beyond taking some classics and combining them to find scenarios where really dramatic changes at late times come into play and change the physics that we believe should have impact on the cosmology we see. And that BDN is already constraining things at around 300 keV, but it could do even better. It's not a done story. And that anomalies like H0 and S8 really are there to be explored. I think that they're real tensions, and I think that models can help make real progress on them. And The important thing is, though, that there are a lot of possibilities out there. We need to be thinking about this actively, and I think that we're going to have a lot of fun in the next decade. Thank you very much.
All right, so we'll open up the floor for questions for Neal, and I guess those on Zoom, if you could raise your hand, and then we'll have you ask your question if it's coming from there. All right, in the room.
So you said that models that try to solve the Hubble tension by having extra energy at early times are now thought not to work. Does that include early dark energy models? And why are they now thought not to work?
So it's going to depend on who you ask. And it's going to depend a lot on what data set you include. Because there are some data sets that will be in very sharp tension, and some data sets that will maybe push you in positive directions. Let me give you an example with this right here, which I didn't go into. But if I take the DES data and the Planck data, Pantheon, all that, right, and ACT lensing, and I put it into this model of this model right here with dark matter interactions and X radiation, okay? That actually gets pulled up. It likes a large Hubble. If that was the end of the story, I would have said it's solved. You want low S8, you want high H naught, you want these interactions, you want to turn off, it would be a great model that would have fit everything. But if you then also added ACT plus SBT, ACT DR4 and SBT 3G, they really don't like additional radiation, and they really pull it down. Okay, and to the point where you can't look at that and say, oh yeah, that's solving the problem anymore. Okay, so different data sets are really pulling you in different directions.
It's not solving the whole problem.
Yeah, and I think that the same thing is true for EVE, for early dark energy, where, for instance, it was pointed out by Colin that there's this very sharp tension with the Lyman alpha forest, and then other people will say, then you can talk to Mark, and he'll say, well, it rules out lambda CDM too. It just rules it out EVE by more. So, so I just, that's what I mean, is I think that I don't know of anything out there right now that doesn't confront some sort of challenge when you put in certain data sets. There's nothing out there that you just throw everything at it, and it could just be that some of these data sets are going to be wrong. And it could be that, of course, the data sets is wrong. It could be the Cepheid normalization. But it could be something like, ACT, or it could be Lyman alpha, or whatever, right? It could be, so time will tell as these, data sets mature, and we'll get better understanding of, and maybe that will help resolve this as we get better understanding of the data.
Actually, how big is the tension now? I thought Wendy's recent data reduced it significantly.
Oh, I'm on camera.
Well, I'm asking a question. Go ahead.
And I'm being recorded. But all I can really say about that is I'm not an expert on that side of things. And there are experts on that side of things who come to very, very different conclusions about what the current size of the tension is.
Wow.
And so some people, I think, will tell you that that tension is still very, very strong, including using an ensemble of different standard normalizations for the supernova. And other people will tell you that it's now ameliorated and it's just a few sigma. But again, I want to come into this, which is I think that part of the nice thing about having a concrete model, whether it's EVE or something like this, is that you can put it in, and all these models make very important, because they influence physics at the EV era. They have signals that are at some level unavoidable in terms of other data sets. So if I think that if you keep on going and you get really good CMB data and you get really good large scale structure data that continues to point in the direction of lambda CDM, and everything points to lambda CDM, then I think just when these models actually confront that data, they're going to have a hard time doing it. So the nice thing I think about thinking about this in that context of how are you really trying to solve this, is that those all ultimately have predictions, and you can test those predictions, and it doesn't have to be the only thing you predict is that Hubble changes.
Yeah, I would respond to that by saying you're a particle physicist, but as an astronomer, I think it's in the Cepheids. I mean, they're notorious. So, if you're a young person thinking about how to solve this problem, you have to think about the Cepheids or all of these things. I say go for the Cepheids.
But I think that there's as Mary Angela said, I've been thinking about various dark matter models and things like that for a while. And the thing that I will say about that is that there have been a number of anomalies that have come and gone, and people have thought about, and but they've been extremely productive in terms of challenging. Particle physicists can travel like a horde, and it really can take something to break that, to break them out of that.
I hadn't noticed that.
Sort of a story to that point is that at one point, SLAC runs the Summer Institute, right? And there was one point, I forget what year it was, but one year I was invited to come give the seminar on exotic models of dark matter. And so I gave them, and then 5 years later, they invited me back to just give the general dark matter lecture. And I had not changed the models I was working on. They were the same models. But it's just, what we consider exotic changes, and but by having a concrete target to confront allows us to open our minds and think, oh, well, what were the assumptions that went into that? What did I really assume when I made that prediction? And you challenge those assumptions and you come up with new and different models, and maybe those things have relevance. And maybe it has ultimately nothing to do, right, with what motivates you to think about it, but helps break you out of your thinking and think about things differently. So I still think that these things are helpful targets.